We're now going to look at NAND implementation. Now, why would we need that? So far all the logic systems you've designed have been made from a combination of different logic gates. So they've been a mixture of AND, OR, NOT, NAND and NOR. And as you know, every single type of logic gate comes on its own separate integrated circuit. So if we've got 4 different types of logic gates in our circuit, we need to have 4 different integrated circuits in our circuit whenever we go to build it. So that's a little bit wasteful, because what we can do is we can make every single different logic gate simply from NAND gates by combining them together in particular ways. So that means that you only need to keep a stock of one particular type of gate, i.e. the NAND gates, which means you can buy them in bulk, which therefore makes your circuit cheaper. Now, if you look in your booklet on page 35, you can see the equivalent NAND gate circuits for each of the different logic gates, NOT, AND, OR and NOR. And sometimes if you're looking at different books or websites, you might see the NAND equivalent of a NOT gate referred to as a NAND inverter. So how do we make a logic circuit made from a combination of different gates simply from NAND gates? So you can look through the first example in your booklet, which is on pages 36 and 37, and I'm going to work through example 2, which is on page 38. So when you look at page 38, so we replace each logic gate in turn. So if we start with input A, so there's input A, and this is an AND gate. So the equivalent of an AND gate is a NAND gate followed by the NAND gate with the 2 inputs connected together, the NAND inverter. Okay, then also going into this we have got B, and it's coming from a NOT gate. So a NOT gate is simply a NAND gate with the 2 inputs connected together, like that. And that's feeding around and up and into the top here. And then at the bottom here we have got input C, which again is going into an AND gate. So our AND gate is made up of the 2 NAND gates, same as we had before. And NOT B is also feeding down into this one. So the only thing we've got left now to draw is our OR gate. So for the OR gate, we have 3 NAND gates. So there's the first one, the second one, and then they go together into a third one. And that's our output Q. So just to recap, we have got our AND gate, which was inside the original little red square on the board. That's our equivalent of our AND gate at the top. We have our AND gate at the bottom, which is represented by this one down here. And then we have our NOT gate here. And this one over here, that's the equivalent of our OR gate. So there's a couple of ways of doing it. You can just draw it straight the way I've done it there, but what you can do is you can draw yourself the boxes in advance, and then inside each of the boxes you can draw the equivalent circuit. Okay, now the final thing we can do, because at the minute when you look at this example you can see that we are using 8 different NAND gates, which would mean we need the complete fill of 2 NAND gate integrated circuit chips. However, there are some NAND gates on this circuit that we don't actually need. Okay, so if you think about it, whenever you have got a NOT gate followed by another NOT gate, okay, so if our input was A, we've got a NOT gate, that means here we've got not A. And back over here on the side, we're back to A again. So whenever we've got two inverters, two NOT gates, one after the other, essentially they are redundant. We don't need them because one cancels the other one out. It's a bit like a double inversion in English. So what we need to look for then in our NAND gate implementation is we're looking for the NAND gate equivalent of this. So we're looking for a NAND gate with two inputs connected together, connected to a second NAND gate with both inputs connected together. And if that's the case somewhere in our circuit, then we can simply put a line through it. So looking at what we have got on the board, for example 2, we have got nothing that we can do with this one because it's got two different inputs. However, following on from there, we've got a NAND inverter, the two inputs connected together, leading on into a second NAND inverter. So that's the same as what we've got here. And that means that those two NAND gates are actually redundant. So the way that you mark this on your diagram is simply to put a line through it. So that's a line going through that one, and that's the redundant one that goes with it. If we look on down the diagram here, this is a NAND inverter here, but it's splitting off and feeding into NAND gates that have separate inputs, so that one has to stay. So does this one down here because it's got two separate inputs. However, moving on across the diagram, you can see here we've got a NAND inverter, followed by a second NAND inverter, the same as we had at the top here, which means we've inverted the signal and then inverted it back again. So these two inverters at the bottom here are also redundant. So we've already marked the first set of redundant gates by putting a single line through them. So to mark the second set, we simply put a double line through it, like so, and that marks those as redundant. So what we've actually got left are 4 logic gates, which means in fact that we only need to have one integrated circuit. So we have saved a whole massive about 40 pence.